Previously, we discussed the entity relationship model. We discussed the basic concepts of the ER model as being entity types, attribute types, and relationship types. In this section, we will zoom into the enhanced entity relationship model, which basically offers some extra modeling concepts on top of the ER model. These modeling concepts allow us to capture even more semantics of the universe of discourse than the plain vanilla ER model. In what follows, we will discuss the EER modeling concepts of generalization, specialization, categorization, and aggregation. Let's start by discussing the idea of generalization, specialization. And to do so, we need to discuss the concepts of superclasses and subclasses. Let me first introduce a very brief example. Suppose we want to build an information system for a university administration. If we focus on the corresponding data model, you will see that you have entity types such as professor, student, and course. Let's zoom into the entity types of professor and student. And let's also have a look at their attribute types. A student has a student number, a student name, a student birth date, a student gender, and a student address. A professor has a professor number, a professor name, a professor birth date, a professor gender, and a professor address. So you can see that student and professor clearly share some common attribute types. What we can now do is we can group those commonly shared attribute types and put them into a superclass. A superclass which we refer to as person. In other words, student and professor become the subclasses of the superclass person. So in many cases, as written down on my slide, a class can be subdivided into different subclasses. In our case, the person class can be subdivided into the subclass professor and a subclass student. A subclass is then a subgrouping of entities, either professors or students, of an entity type, in our case person, that are meaningful and need to be represented explicitly because of their significance to the database application. In other words, in our setting, it is important to distinguish between professors and students. A superclass is an entity type which groups different subclasses. Think about the person superclass, which groups the subclasses of professor and student. An entity that is a member of a subclass, remember, professor or student, inherits all the attributes and relationships of the superclass. So in our particular case, this means that a student inherits all the attribute types of person, but also a professor inherits all the attribute types of a person. An entity that is a member of a subclass should possess attributes which represent the specific characteristics of that subclass. For example, in our case, a professor will have specific attribute types, such as date of PhD, when the professor obtained his or her PhD, and academic degree, whether the professor is an associate, assistant, or a full professor. Those are attribute types which particularly relate to the professor subclass, but not to the student subclass. Another example you can see right here. We can have a superclass employee. This is a very general class with attribute types such as social security number, employee name, gender, date of birth, and so on. Within this very general superclass, we can then start identifying subclasses. Subclasses such as salaried employee, which receives a fixed salary, hourly employee, which is being paid by hour, and contracted employee, which basically has a contract. What are the advantages of coming up with a generalization specialization relationship now? Well, the advantages are as follows. It is likely that employees of a certain subgroup, either salaried, hourly, or contracted, do not have the same characteristics as employees of another subgroup. In other words, by doing a generalization, specialization, we can further refine semantics. Because for each subclass of employee, specific characteristics can be determined so that the subclass can be distinguished from another subclass. Remember the example I also gave earlier with person into student and professor. A professor can have special attribute types which are not shared by a student. A student can have special attribute types which are not shared by a professor. So it allows us to refine, it allows us to add very specific semantics to each of the subclasses. And when we say very specific semantics, we are not only referring to specific attribute types, but we are also referring to specific relationship types. As indicated by the second sub-bullet, it is possible that some relationships only exist for some groups of employees. By representing the groups explicitly, one can enforce which relationships are relevant for which employees. Translated to our student-professor example, a professor can have a relationship to course. This relationship is entitled teaches. A professor can teach courses. A course is taught by one or more professors. Obviously, students cannot teach courses. They can register or subscribe to courses. So different relationship types with the course entity type can then be defined between professor and course and between student and course. So by doing this, generalization, specialization, further semantics can be added to your model. So what is now the difference between specialization and generalization? Well, both refer to the same thing, except that generalization looks at the process of abstraction, whereby we suppress the differences among several entity types, identify their common features or attribute types, and generalize them into a single superclass. This is what we refer to as bottom-up synthesis. In other words, what do we mean with generalization? Generalization is the process whereby you go from student and professor to person. This is bottom-up synthesis. Right? So if you move from the subclasses to the superclass, this is what we call generalization. Specialization is the other way around. Specialization is the process of making the differences between some entities of an entity type explicit and defining a set of subclasses of that entity type. So if we would move from person to professor and student, then this is what we refer to as top-down analysis or specialization. As we already said, when you're doing specialization or generalization, both attribute types and relationship types of the superclass will be inherited by the subclasses. Translated to our professor-student example, it means that both professor and student will inherit the attribute types and relationship types of the person superclass. A specialization generalization can then be further qualified by means of the disjointness constraint and the completeness constraint. A disjointness specialization specifies that an entity can be member of at most one of the subclasses of the specialization. Applied to our example of person specialized into student and professor, this means that a person cannot be a student and a professor at the same time. This would be a specialization which is disjoint. An entity can only be member of at most one of the subclasses. Alternatively, as we will see later on, you can also have specialization-generalization relationships whereby you have overlap. Overlap means that the entity can be member of more than one subclass at the same time. We will see some examples later in the session. A completeness constraint qualifies the completeness of the specialization. A total specialization specifies that every entity in a superclass must be a member of some subclass of the specialization. In our example of person being specialized into professor and student, this would imply that every person is either a professor or a student. If this specialization is total, As I said, it would imply that every person is either a professor or a student. If the specialization, on the other hand, would be partial, it would allow people to exist or persons to exist which are neither a professor nor a student, which in other words do not belong to any of the subclasses. Let's work out some examples of this. Here you can see an example of a specialization. Product is the superclass and it's being specialized into finished product and assembly product. By the way, when doing a specialization, you can always apply the is-a test to identify the subclass. A finished product is a product. Hence, finished product is a subclass of product. An assembly product is a product. Hence, assembly product is a subclass of product. Product can have attribute types and relationship types, which are not depicted here, but which will be inherited by finished product and assembly product. Assembly product adds an extra attribute type, which represents the assembly time, the time needed to assemble the product. A finished product has also a special relationship type to supplier. The relationship type is referred to as supplies. A finished product can be supplied by at least one, at most n suppliers. A supplier can supply at least 0, at most n finished products. A supplier has a supplier number and a supplier name. The relationship also has attribute types such as delivery period and purchase price. Let's now look at the qualification of the specialization. This is a specialization which is total, T. A product is either a finished product or an assembly product. All products are one of these. There are, in other words, no products which are neither a finished product or an assembly product. The specialization is also qualified by D from disjoint. That means that a product is either a finished product or an assembly product. It cannot be both at the same time. So you see the T and the D allow us to further specify the generalization specialization, allow us to further qualify it. So in other words, it allows us to add more semantics to the model. Where do we get the T and the D from? Well, we get the T and the D from our business expert. Our business expert will tell us whether a product can at the same time be a finished product and an assembly product, and whether all products are either finished or assembly products. So by talking to our business expert, we can clearly qualify the generalization specialization. Let's look at another example. Here you can see artist, which is being specialized into painter and sculptor. We always apply the is-a test to identify the subclass. A painter is an artist. This is correct. So painter is a subclass of artist. A sculptor is an artist. This is a correct statement. So sculptor is a subclass of artist. Artist can thus be specialized into painter and sculptor. Remember, specialization is top-down analysis. Generalization is the other way around. This is bottom-up synthesis. Let's now have a closer look at the qualification of the specialization. This specialization is partial. Partial means that, according to our model, there are artists which are neither painters nor sculptors. Think of musicians, for example. A musician is an example of an artist which is neither a painter nor a sculptor. So the specialization is partial. The specialization is also overlapping, O. This means that an artist can at the same time be a painter and a sculptor. Think about Leonardo da Vinci, for example. He was a painter and a sculptor at the same time. In other words, this is an example of a specialization with overlap. One more. Actually, you can apply multiple specializations on the same superclass, and you can see an example of that here. You see that employee has first been specialized into secretary, engineer, and technician. This specialization, is total and disjoint. So it means an employee is either a secretary, engineer, or technician. There are no other possibilities here. This specialization is also disjoint. A secretary cannot be an engineer or a technician. There's no overlap there. Another specialization specializes employee into manager. Manager is a subclass of employee. Let's apply the is-a test as we always do. A manager is an employee. Hence, it makes sense to add manager as a subclass of employee. This is a partial specialization indicated by P. A manager can work on 0 to n projects. A project is assigned to minimum 1, maximum n manager. A project is assigned to minimum 1, maximum 1 manager. So exactly 1 manager. Remember, as discussed extensively earlier on, a minimum cardinality of 1 refers to, indeed, existent dependency. And then we have a third specialization, which is going to specialize employee into permanent employee and temporarily employee. This is a total specialization which is disjoint. A temporarily employee can and also be related to a mandate extension. Temporarily employee can get 0 to n mandate extensions. A mandate extension is always related to minimum 1, maximum 1, so in other words, exactly 1 employee. Two very important concepts when talking about specialization and generalization are the ideas of a specialization hierarchy and a specialization lattice. In a hierarchy, as you can see it in organizations, you can have at most one boss. So every subclass participates as a subclass in only one superclass-subclass relationship. In other words, a subclass has at most one superclass. In a specialization lattice, a subclass can be a subclass in more than one superclass-subclass relationship. In other words, a subclass can have more than one superclass. In this case, you can have multiple inheritance, and we're going to illustrate this in what follows. Here you can see a specialization of person into employee and student. We again do the is-a test. An employee is a person, a student is a person. This specialization is total and overlapping. In other words, it means that a person can simultaneously be an employee and a student. Employee is then further specialized into staff, faculty, student assistant. Student is further specialized into student assistant, graduate student, and undergraduate student. Worth noting here is that student assistant has two superclasses. In other words, a student assistant is an employee, and a student assistant is a student. A student assistant is going to inherit attribute types and relationship types from both employee and student. This is what we refer to as multiple inheritance. Multiple inheritance refers to the phenomenon whereby a subclass is going to inherit from multiple superclasses. Student assistant can then be further specialized into research assistant and teaching assistant. This is then a specialization which is total and disjoint. This finishes our discussion of the first extension of the EER model, which was the idea of specialization, top-down analysis, or generalization, bottom-up synthesis. The EER model also has an extra modeling concept, which is what we refer to as categorization. With categorization, we will model again a superclass-subclass relationship with more than one superclass, where the superclasses represent different entity types. In this case, the subclass will represent a collection of entities that is a subset of the union of the entities of the superclasses. We call such a subclass a union type or a category. This may sound very complex, so you know what we're going to do? We're going to work it out with a small example. Here you can see on my next slide, you see the ideas of selective inheritance and total or partial categorization, but it's a lot easier if we work it out with this example right here. Here we have two superclasses, natural person and legal person. And let's just say that we work out a very small example. So with natural person, we have, for example, John Smith and Sarah Adams. John Smith and Sarah Adams are two examples of natural persons. For legal person, we look at IBM and Microsoft. An account holder is a category, is then a subset of the union of the entities of the respective superclasses. So in this particular case, the account holder can consist of entities such as John Smith and IBM, right? So it has two different entities, an entity being a natural person and another one being a legal person. So the category subclass in this particular case is a subset of the union of the entities of the superclasses. Here, when you do categorization, you have the idea of selective inheritance. Selective inheritance means that some account holders will inherit attribute types and relationship types from natural person. Other ones will inherit attribute types and relationship types from legal person. So selective inheritance refers to the situation whereby the account holders either inherit from natural person or legal person. The question now is, can we not solve this using a classical specialization generalization? Remember, in order to solve it with a classical generalization specialization, you need to apply the idea of the is-a test. Let's see whether it works out in a particular way. An account holder is a natural person. That's not true, because you can have account holders that are legal persons. An account holder is a legal person. That's not true, because you can have account holders which are natural persons. So account holder cannot be a subclass of either natural person or legal person. Let's see whether we can apply the is-a test in the opposite direction. A natural person is an account holder. That's not true, because you can have natural persons that are non-account holders. A legal person is an account holder. That's not necessarily true, because you can have legal persons that are non-account holders. Note, however, that the categorization can also be total. In our case, the categorization is partial. You can see the P there on the plot, which refers to the fact that the categorization is partial. So as I said earlier, you can have natural persons that are non-account holders and legal persons that are non-account holders. If, however, the categorization would be total, it would imply that all natural persons are account holders and all legal persons are account holders. In this particular case, the is-a test can be applied, because if the categorization is total, then a natural person is an account holder and a legal person is an account holder. So in this case, we can work it out with a classical generalization specialization, whereby we make natural person a subclass of account holder and legal person a subclass of account holder. So you see, in case the categorization is total, we can solve it with a generalization specialization. In case the categorization is not total or partial, then we cannot solve this using a classical generalization specialization. In our example, you can see that account holder then has its own relationship type with bank. An account holder is connected to at least one, at most n banks. A bank can have at least one, at most n account holders. So you can see categorization is another EER modeling concept, which allows us to add even more semantics to our conceptual data model. A third and final building block of the EER model is aggregation. Aggregation refers to the activity of building composite objects. A composite object is based upon grouping a number of entity types and their relationship types. A composite object can then have its own attribute types and relationship types. Let's provide an example of that. Well, here you can see, first of all, two entity types, job and applicant. Let's just first read the EER model. For a job, I can have 0 to n applicants. An applicant applies for minimum 1, maximum n jobs. As always, remember, minimum cardinality of 1 refers to existence dependence. What we have now done here is we have grouped job and applicant into an aggregated construct, which is called interview. The combination of a job and an applicant gives me an interview. That's an aggregated construct. At the level of this aggregated construct, we can now define attribute types or separate relationship types. In my example, I could add an attribute type duration to the interview construct. This will then specify the length of the interview. Besides adding an attribute type duration to the interview aggregate, I can also define a separate relationship at the level of the aggregate. So here you can see a relationship between interview and job offer. An interview can lead up to minimum 0, maximum 1 job offers. Vice versa, a job offer is usually based upon minimum 1, existence dependency, maximum 1, so that means exactly 1 interview. So the EER model gives us some more building blocks according to which we can add even more semantics to our ER model. The building blocks that we discussed were 1. Specialization, generalization, 2. Categorization, and 3. Aggregation. Those can now also be applied to our personnel administration example we discussed earlier. Let's see what happened here. So you can see manager has been added as a separate entity type, and it's related to the employee entity type. In fact, manager is a subclass of employee. Let's apply the is-a test. A manager is an employee. So that's why it makes sense to specify or define manager as a subclass of employee. Is the specialization total or partial? Well, let's just verify that. An employee does not always need to be a manager. Typically, only a few of the employees will be managers. Hence, it makes sense to qualify the specialization as partial, since not all employees will be managers. Then we have also an aggregation that we have applied. A department is in charge of minimum 0, maximum n projects. A project is assigned to minimum 1, maximum 1 department. So that refers to exactly 1 department. What we've done here is we have aggregated department and project into an overall composite, into an aggregate, which we call assignment. At the level of this aggregate or composite, as we already said earlier, you can then define attribute types and relationship types. Here you can see that the relationship type works on has been defined at the level of the aggregate. So the aggregate assignment, or the composite, is then related to employee using the works on relationship type. So you can see in the ER model, we can even add more semantics to our ER model than just the basic entity type, attribute type, and relationship type constructs. We can add generalizations, specializations, categorizations, and aggregations. Basically, the drawbacks that we already discussed earlier on with the ER model also remain applicable here. That means that temporal patterns cannot be modeled here. Remember, earlier on, we explicitly mentioned the fact that you cannot model that an employee needs to be assigned to a department after 6 months, for example. Well, here you can also not model that. Also, integrity rules which span multiple relationship types cannot be modeled. We cannot enforce that an employee should always work on projects assigned to the department where the employee belongs to. So you can see that many of the drawbacks, or actually all of the drawbacks of the EER model, still apply here as well in our enhanced entity relationship model. To summarize, both the ER and the EER model are very good conceptual data models. Why? Because they allow us to model the universe of discourse in a user-friendly way by focusing on concepts which are clearly understood by the end user. So an end user can very easily read an ER model and verify it to see whether all the semantics of his or her business context is appropriately captured in the ER model. Obviously, this ER or ER model needs to be given then to an IT person, a database designer, in order to build a database application. For this purpose, the ER or ER model will be mapped to a relational model. We will discuss relational models in a next section.